Welcome to a new mini-series. This series is going to cover applications of machine learning in econometrics. If you've been following this channel, you might recognize that this is a departure from the main topics that we've been focusing on, namely structural modeling and discrete choice models. And because of machine learning's complementary status with econometrics and its growing importance as time goes on and data demands get larger, I thought it would be useful to also cover this topic on this channel. So over the next several videos, we'll introduce the basics of machine learning and also go through several recent papers that have applied machine learning methods into econometric analysis. And my hope is that by going through these videos, you'll be inspired to come up with ways to constructively involve machine learning in your research pipeline and also have a better understanding of the truly complementary nature that these two approaches provide each other. And to start, I want to just discuss what do we mean by machine learning, go through some basic vocabulary, and hopefully this will form a decent basis for going a little bit further down this line. To start with, what is machine learning? You'll probably find a bunch of other definitions online, but according to me, the definition is we allow the computer to recognize patterns on its own without being explicitly programmed for every possible contingency. A prime example of this is the United States Postal Service, which has computer vision tools to automatically sort mail. And the computer vision comes into play in recognizing the address and the zip code where the piece of mail needs to be sent. So the computer has recognized the pattern of what constitutes a number 9 versus a number 7 versus a number 4. And we don't have to provide a case-by-case guidance about which number is which. Other examples come from Google with its AlphaGo Zero program, which became better than the best human player at the game of Go. And other examples include voice assistants. These have recognized patterns in sound waves and been able to convert that into a format that's meaningful for the computer to understand and then respond back appropriately. Now, if we contrast machine learning with artificial intelligence just refers to systems that are performing tasks that traditionally would require human intelligence to do. And by human intelligence, we mean things like reasoning or perception or decision making. And machine learning is a key way to build these AI systems. But it's not the only way that we can develop AI. And now that we have this broad understanding of machine learning, let's now think about how machine learning applies to statistical analysis, which is most closely related to econometrics. And if we think about analyzing data, there's kind of two main reasons that we would want to do this. One is for prediction, and another is for inference. And with prediction, we just want to get a y hat from a given set of x's. But with inference, we want to know how does changing x affect y. And so maybe an example here would be house prices. So I can just say, give me data on house prices. I'll come up with a function to predict the house price given the characteristics of the house. But then the inference question might be, well, what would it be worth to me to remodel my bathroom? How much more is that going to get me in terms of home value so that I can personally understand whether that's a good investment or not? And connected to these ideas are three different types of inference according to Andrew Gelman, who's a statistics professor at Columbia University. And he says that one type of inference is generalizing from sample to population, and we typically refer to this as statistical inference. Another type of inference is generalizing from the control state to the treatment state, and we typically call this causal inference. And then a third type has to do with measurement error, which just says that observed measurements are noisily capturing the true underlying constructs of interest. So if you think of IQ and the factor model material we talked about in a prior video, that would fit here. And philosophically, each of these types of inference can be framed as a prediction problem, and that can be useful to think about how these connect to each other and how machine learning and econometrics connect with each other as well. So going a little bit farther with this idea from Professor Gelman, how can we actually frame each of these types of inferences as a prediction problem? Well, with statistical inference, we want to know what's y or beta going to be in a different sample. This is your classic intro to statistics, t-test, all that. With causal inference, we want to know what would the outcome be if we switched each person's treatment status from what it actually was. So this has to do with the potential outcomes model of causal inference. You can check out Scott Cunningham's Mixtape textbook if you want to know more about that. And then with the measurement quality, we want to know what y would be if we could perfectly measure the underlying constructs. So that's just a little bit about philosophically how econometrics and machine learning might differ. So hopefully you're seeing that there's some similarities and some differences between them. And then I wanted to talk a little bit more about the differences between them just in terms of vocabulary and the way that different variables are labeled in these two disciplines can be different. And so it can be helpful to have a little dictionary or a Rosetta Stone converting the two so that you can better understand these concepts if you want to do your own reading in machine learning territory. So the y variable, the dependent variable as we call it in econometrics, that is referred to as the target variable in machine learning. A covariate or an independent variable is referred to as a feature in machine learning. An observation or a row of data is called an example or an instance in machine learning. What we call the objective function in econometrics is referred to as the cost function or the loss function in machine learning. And then what we call estimation in econometrics is referred to as training or learning in machine learning. And machine learning is all about automating two hand-in-hand processes. The first process is what's referred to as model selection, which in econometrics parlance, we would say the model specification. And in econometrics, we typically have some theoretical reason for asserting a particular specification. But in machine learning, the researcher is much more open to what the right specification could be. And so you can think of several dozen potential models and selecting the best one out of all of those. And then the second process, which we've talked about in the past in this video series, is called model validation. And this is just a question of how well does the particular specification that we chose generalize to other similar contexts. And in machine learning, we want to automate these two processes in such a way that we get maximum predictive accuracy as defined by whatever our cost function is. So if it's a regression problem, we want to maximize R squared or minimize the mean squared error. If it's a classification problem, then we might want to minimize both the type 1 and the type 2 error rate or so forth. And just keep in mind that this goal of machine learning is quite different than the goal of econometrics, which is causal inference. Another subtle difference between econometrics and machine learning is how much of the data set is being used for estimation. In econometrics, we typically use the entire data set for estimation. But in machine learning, because model validation is taken so seriously and it is done in an automated fashion, the best practice is to hold out some of the data to use to validate the model. And so you're only going to train the model on a subset of the data. And then depending on the application, you might also want to hold out some data for testing purposes to evaluate how well your validated model would work in a new context. So typically we earmark 60 to 70% of all of the data that we have for training purposes. And then we hold out 10 to 20% for testing. And we also hold out 10 to 20% for validation through a process known as cross-validation. And we'll talk more about this in upcoming videos, but just to try to help you understand the main differences between econometrics and machine learning, that's the goal of this video. And then to make sure that there's no misrepresentation of your data, the splits should be done at random to determine which observations are in which of these three sets. And the splitting should also respect the process by which your data was generated. And by that, I mean, if you have panel data, you shouldn't be putting 2 time periods of the same person in one set and then 3 time periods from the same person in another set. You should be dividing this out on the basis of people, not time observations within a person. So that is a little bit about how machine learning and econometrics are different but similar. And in the next video, we'll talk about something called the bias variance trade-off. which is a fundamental trade-off that machine learning practitioners face when wanting to do this automated model selection and validation process. Having a little better understanding of how machine learning works will help us as we push further on to see how machine learning methods can be contributing to econometrics. So I hope to see you in the next video.